Welcome back to our discussion of computer network protocols. Today we arrive at the layer right in the middle of the 7-layer ISO OSI protocol stack, layer 4, the transport layer. Recall that the purpose of the transport layer is to enable two processes to talk to one another. Typical example is where a client talks to a server, receives responses back from that server. To make it somewhat more specific, think of a web browser that is connected via the transport layer to a web server. The fact that the transport layer is in the middle of this protocol stack is not coincidental. It provides an interface between the upper 3 layers of the protocol stack and the lower 3 layers. Recall that the upper 3 layers are application-oriented. They tend to cater to the needs of the application. The lower 3 layers are network-oriented. They deal with the operation of the network itself, how to transport, how to get a message from one end in a network via several intermediate nodes to the other end. What this means on an abstract level is that the application-oriented layers know that they will have some sort of a pipe or a connection on layer 4 that they can use to communicate with one another without having to care about the network infrastructure. Similarly, the bottom 3 layers, the lower 3 layers, know that whatever infrastructure, whatever mechanisms exist, they have to provide some sort of a pipe or a connection so that the upper layers can utilize this pipe or connection on layer 4. I've used quotes around pipe and connection because these two terms have rather specific meanings in the context of the transport layer, which you will encounter soon enough. One of the recurring themes that you will encounter throughout all 3 of the videos on the transport layer is that of reliability. Reliability also has a specific meaning in the context of the transport layer. And whenever we talk about the transport layer, you should listen carefully, because if you are able to talk about reliability on layer 4, you will have quite a lot to say about the operation of the transport layer. So what the transport layer needs to achieve is to enable a process on one machine to talk to a process on another machine. A little picture like this may depict it. If that's our one computer and that's our other computer, a process will be running on this machine, a process will be running on that machine. For the sake of illustration, you may think of the process on the left as a web browser, the process on the right as a web server. Somehow, the infrastructure beneath layers 1, 2, and 3 will facilitate communication between the two computers. What the transport layer needs to do is to identify the processes. So if this is process A and that's process B, the transport layer needs to enable process A to say, I want to talk to process B. And so some sort of identification of the process you want to talk to is required. One of the specific questions we have to ask is, what sort of connection do we need between these two processes? Phrased a little differently, what is the quality of this connection? Or to use the correct term, what is the reliability that we require for this connection between the two processes? Reliability has a very specific meaning in this context. Reliability refers to an attempt to make sure that communication happens, but more importantly, it refers to the fact that if something goes wrong, the communicating parties will know that something has gone wrong. They cannot communicate and messages are lost and whatever, and they don't know about that. So a reliable connection is one where we know that what has been communicated has indeed been communicated. One way to think about this, to help us to think about this, is a little graph where on the one axis we ask about the need. By need, I mean, what does our application on top need? What quality, what reliability does it need? And let's say choice ranges from low to high. On the other axis, we may wonder about the context. And by context, I'm referring to the infrastructure, what is provided in our world. And let's say that ranges from poor to good. To illustrate what I mean by this context, poor to good, it's possible that we may, at the physical layer, use optical fiber. And we know that if we transmit something via optical fiber, it gets to the other end. Hardly anything goes wrong ever, unless the fiber is broken, and then the protocol is not going to fix that. In contrast, if we use radio waves, then all sorts of interference are possible, and we may have a very poor connection quality between the two parties that are communicating. But it does not only depend on the medium that we're using. It also depends on what the other protocols do. Remember, we are talking about layer 4. Now, layer 3 may attempt to rectify problems. Layer 2 may attempt to rectify problems. The medium on layer 1 impacts on the quality. So if we are correcting problems on layer 2 and correcting problems on layer 3, then it may be very reliable on layer 4 already. So we may have a good infrastructure because of either the physical circumstances, like the medium that we're using, or it may be because of the lower layer protocols. Let's quickly talk about the need between low reliability and high reliability. In some cases, you want whatever you send via the network to arrive at the other end. Think about financial transactions. If you are moving money from one account to another account, you want to be sure that transfer, that message has gone through properly and was received properly at the other end, or otherwise you have to know that it did not go through and that the transaction did not occur as you thought it had. So there, clearly, you need a very high level of reliability. On the other hand, if you think about things like video streaming, if you lose a frame or two every now and again, it's not all that important. In fact, with speech, you can lose quite a number of frames, and you can still understand the speech. So for that sort of transmission, maybe you don't need a good option. Maybe some sort of connection is better than no connection at all. And we should also keep in mind that the cost of achieving a high quality is often, it's often expensive. And therefore we may want to forego the cost because the low quality will be sufficient. We'll make this example clearer when we get to the actual examples of protocols as we move along. Talking about actual examples, There are two primary examples that we will discuss on layer 4, and that is TCP, the transmission control protocol, and UDP, the user datagram protocol. And we'll get back to those two in a moment or two. But before we go to those two, when the ISO OSI model was initially developed, the developers realized that you had to deal with different contexts, different needs, and they proposed a number of transmission protocols. The protocols were called TP1 and TP2 and TP3 and so on. You don't have to remember that because those protocols are dead. No one uses them. But the protocols catered for the sort of conditions where you needed something poor or needed low quality and you had a poor infrastructure, or you needed something where you had a poor infrastructure but you needed high reliability, or you had a very good infrastructure and you needed high quality. And you could then pick a protocol that would work for you. And in particular, you could pick a protocol that would be cost efficient, because if you have a good infrastructure, you're not going to spend as much time checking up on everything and attempting to correct everything. Now, the two example protocols that I mentioned, TCP and UDP, don't really look at the context at all. They simply ask the question, do you want that to have low reliability, or would low reliability be sufficient, or do you need high reliability? And that's something that you will see coming through as we discuss these protocols. One of the notions that is very often used to refer to one aspect of a reliable protocol is the question whether that connection is connection-oriented or connectionless. What we mean by connection-oriented is that a connection is established between the two parties that are communicating, between the two processes that are communicating. So you establish the connection, you use that connection to communicate, and then you terminate the connection. The connectionless option, on the other hand, is one where you do not establish a connection beforehand. You just start talking and you hope that the various parts of your message will get to the other end, and if there are responses, you hope that they will get back. But there's no pipe as such. There's nothing that is set up beforehand. In terms of connection-oriented, the example that is typically used for that is a telephone call. If you think about the typical telephone call, then you would phone someone, you would know whether the connection is established properly, and you will be able to communicate up to the point where you've reached, where you've achieved communication, and then you will hang up the phone. So if you think about the way in which that protocol works on a normal telephone, then it's really on two levels. When I pick up my phone, I hear the dialing tone, and that tells me that the line is available to be used. And then I dial my number that I want to call. I hear the phone ringing. If the other party doesn't answer, they're not home, and this connection has failed. If they do answer, I typically hear them answer. I hear that the phone is picked up, so the ringing stops. But then we tend to go into a second stage of this protocol. The person who answers the phone typically says hello, or your person's name, or whatever needs to be said to say that that person is ready to communicate. And that person may say, John here, or whatever. And then on my side, I will say, hello, John, how are you? And John on that end will say, I'm fine, thanks, how are you? And I will say, I'm also fine, thank you. Very often we don't really care whether the other person is fine or not. We just want to test this channel to see whether it's working. And yes, sometimes people misunderstand that, and when you ask how are you, they really tell you. Okay, let's ignore that. In terms of our protocol, we are typically using this exchange initially to set up the communication, to be able to talk to one another. Connectionless is typically compared to a postal system. A postal system that works, so not necessarily one like the one we used to. So a connectionless system is one where you write your message, you put it in the mail, and the next day or so it is delivered. You don't know that it's been delivered, but if the system works, it will be delivered. If something's gone wrong, then you won't know about it. The recipient of that letter may respond to that letter and may write back, put the letter in the mailbox on their side, and a day or two later it will be delivered on my side. And again, that person who sent the response doesn't know whether it reached me successfully. Another way, perhaps an easier way, if you want to think about the speed, email is a nice example of a connectionless service. Again, as an analogy, not as a layer 4 protocol. If I send an email, it's possible that a spam filter will eat the email somewhere, and it may never reach the recipient. Or it may end up in the email box of the recipient, but the email recipient has millions of messages and never reads it. So communication has not occurred. And the same if that the recipient indeed does answer, and the response doesn't get back to me because it's eaten by a spam filter, or because I don't read it, then again, communication has not occurred. So connection-oriented obviously gives you reliability. Not everything we need for reliability, but reliability in the sense that if something goes wrong, we will probably know it. Connectionless, like email, we don't know whether it worked. If it's a good system, it will work, but we have no guarantees. And when something goes wrong, we do not know that something has gone wrong. So our first part that we will explore in more detail is how connections are set up in a reliable manner. And without giving away too much, we can say that TCP, the Transmission Control Protocol, is an example of a connection-oriented protocol. And we will look at how a connection is established in TCP. UDP, the other example that we mentioned, is connectionless. So no connection is ever set up. I can't give you an example of how a connection is set up. A UDP packet, or more technically correct, a UDP datagram, is simply sent away, and we're holding our thumbs and hoping for the best. So let us now turn our attention to how a connection is set up in TCP in a reliable fashion. In other words, to keep on repeating what I've said a couple of times, set up in a manner that we will know whether that connection has been set up or not. While we're talking about setting up or establishing the connection, we also have to begin to think about how will we know that the connection remains working. In other words, during the communication. That will actually be the topic of the next video. But a third thing that will also be mentioned in this video is how do you terminate the connection such that we know that the connection has indeed been terminated. So let's set up a connection between two processes in a reliable way. So we are talking about TCP here, Transmission Control Protocol, and we have a process A here, and it wants to establish a connection with process B. The way in which it happens is process A says to process B, I want to talk to you. And then process B may say, no, I don't want to talk to you, but let's assume that we are going to establish this connection. So process B says, okay, let's talk. Now, if you think about what we know at this stage, what process A knows is that process B knows about this connection and is indeed willing to participate. But process B knows that A wants to communicate, but since B said, okay, let's communicate, B has heard nothing back yet. So B does not know that A knows that both parties are willing to communicate. So what happens next is A sends another message to B to say, okay, let's really talk. So what we have at this stage is a process A that is said to B, let's talk, and B said it's okay. So A sent out a message and received a response back. And process B said, okay, let's talk. And then it got the message from A that said, yes, let's really talk. So B knows the pipe or the channel, the path is open from it to A and back. And A also knows the path from it to B is open and back. Now the messages that are sent have very specific names. When A wants to talk to B, it sends a syn message, synchronize. When B says, yes, let's talk, B says, ack, yes, I heard you, I acknowledge your attempt to talk to me, and also syn. So it says, yes, I want to talk. So I acknowledge and I want to talk. And then process A says, okay, so that's step 1, that's step 2. And in step 3, process A says, acknowledge. I got your message loud and clear, so we can talk. And what we have here is the famous three-way handshake. So three-way handshake in TCP is used to establish a connection in a reliable manner. The two processes now know that they want to communicate, and they can proceed from here, and just while they are communicating, make sure that the connection keeps on working. As we said, there are typically these 3 phases: establishing the connection, then during the communication, topic of our next video, and then the goodbye, the termination of the connection. Now, to terminate it, the designers of TCP thought it good to again use a 3-way handshake. So the handshake to say goodbye is that in step 1, let's say process A wants to terminate the connection, it will say goodbye, and it says it by sending a finish message. Process B in step 2 will say I heard you, but also I'm also done talking to you, so fin plus and then process A in its final message says So I got your goodbye, And what we have again here is that when process A says, I want to terminate this message, it gets an acknowledgement from B to say, yes, let's terminate this. So the goodbye has gone out and it's come back. And B, by acknowledging the fin, says, yes, let's terminate this message, and then it gets an ACK back, so it also knows that the connection has been terminated successfully. Tiny question for you to think about. Suppose this final message gets lost. Then B never knows that this communication has been terminated, this channel has been torn down. And the way it handles that is basically with a timer. Once it says fin ACK, starts the timer, and when the timer runs out and it's heard nothing back, it assumes A is no longer talking to it anyway, and it forgets about the connection. So this is the goodbye. We've seen the hello. What we still need to talk about is the how do we keep the connection reliable while we are communicating. That will be the topic of the next video.